Well, hello Science 9. I'm going to go over some stuff with you today through this video. So you can watch this as you're kind of doing it. Yesterday we were working on this lab. And I thought I'd just touch base to make sure that everybody's getting the dimensional analysis piece correct. Again, most of the packages I think started with 150 calories, but that was our food calories. So if we start with 150 food calories, I showed yesterday the dimensional analysis, or the domino that we would play to get from food calories to kilocalories. And in every one food calorie is equivalent to 1 kilocalorie. So that's going to get you into your kilocalories. To go from kilocalories to science calories, we have to know which one's bigger, and a kilocalorie is bigger. There are 1,000 calories in 1 kilocalorie. And then finally we have to get into joules. So again, we're going to convert our calories to joules. And if you look on your formula sheet on the back on the conversion side, it says that 1 calorie is equal to 4.184 joules. So now that's how we get our answer for joules in the package. So that's our package for our joules. Now to find your energy per gram, all you had to do was take this energy, divided it by the mass. So take this one, our joules, and divide it by our mass in grams, and that's how we'll get energy per gram. Now I know that we got to this point right here where the specific heat of aluminum is going to be a needed number. And so some of you found this in your notes, some of you maybe did not. I thought this is a good time right here to kind of take a break. Let's have you go ahead and find your notes for 9.1, okay, and open your notebook up, and then I'm going to go ahead and flip open to the textbook. For 9.1. Okay, so again, as we kind of go through, we talk a little bit about the differences between heat and temperature. And we know that heat is going to flow from warmer objects, okay, or something that has a higher amount of energy to one that has a lower amount of energy. So the energy flowed from the chip into the can because higher energy was there, lower energy there. Okay, so we know that we were going through that. We know that there are some different units that we like to use. Okay, so we talked about joules. We talked about a calorie and what a calorie represents. Okay, again, this tells us that we have, this is our other unit, which was our BTU. So we had 3 different units for energy. Okay. And then we can then look at the equivalence to them. So there's our equivalence chart. So 1 calorie is 4.18. They said 6, but I always do 4.184. But that's the number of joules, okay? We know that kilocalories are equivalent to calories, so there's our different conversions for energy. Now when we get back here to the next page, we know that as we went through this, we looked at specific heat. So this is the heat that's required to change the temperature of an object. So the temperature increases of an object depends upon its mass and the material that it's made of. And we saw that the other day because we did the mass difference, so like large quantity of water versus small quantity of water, and we did the metal versus the water. So we know that it's the amount of energy that's needed. So like even here, like they say, you need to add 4,184 joules of heat to 1 kilogram of water to raise that temperature 1 degree Celsius. So that's a lot of energy that you add to that mass in order to get the temperature to actually change. Now all of this leads us into this value that we call specific heat. And every material has its own specific heat. So there was a table in our book. I can't see if I can get it on the camera here. Okay, this table right here, okay, gives us the value for like water. So water specific heat is 4,184 joules per kilogram degree Celsius. Now in our lab, we wanted this value to to be in joules per grams degrees Celsius. So when we look at a number, if we are just comparing grams to kilograms, so if I got, this is joules per gram degrees Celsius compared to joules per kilogram degrees Celsius, well, we know that that's just a factor of 1,000. So if I have a 4,184 joules per kilogram degrees Celsius, then that would be the equivalent of our 4.184 joules per gram degrees Celsius, because it's just the kilogram versus the gram, so it's 1,000, shift the decimal 3 places, and that's how we get that value. Now, I noticed that in the chart in the book, they said the specific heat for aluminum is, let's see if we can get that on the camera here, is 900 joules per kilograms degrees Celsius. So when we wanted this now to be the specific heat of aluminum in joules per gram degree Celsius, it would be, shift the decimal 3 places, so that 900 becomes 0.9. So there's our specific heat for aluminum. Now you're going to need this later in the lab calculations. Okay? So again, different materials will cause us to have different specific heats. So some things tend to heat up quicker than others. It all depends upon the particles and how the particles' connections are. We do know that water, though, as a liquid, requires a lot more energy because it has a high specific heat, where something like our aluminum has a low specific heat, so it heats up fast. Okay. Now this brings us to this in our notes. You should have this heat equation in here. Okay, so this is our heat equation, and I thought I'd go ahead, just making sure my camera's working. Thought I'd go ahead and do this on some paper so we can look at this one. So if you wanted to add this to your notes, this would be good. So E is our heat energy, is equal to M, the CP, which is specific heat, times the change in temperature. Now, I like to write it this way, so E equals MCP triangle T, because remember that triangle T is the same thing as a change in temperature. Now, if we set it up this way, that means that we can equate this into a triangle. This is a 3-part triangle where we have our mass, we have our specific heat, we have our change in temperature, and then we have our energy. Okay? So again, this is the heat energy measured in joules. This is your mass measured in whatever value we'd like. So sometimes it's in kilograms, sometimes it's in grams. I tend to stick in grams because we deal with small things. This is our specific heat. And here's where our units differ. So if this is in joules per grams degrees Celsius, we want to make sure that the unit here matches the unit there. So you have to make sure that these match. So if this is in kilograms, this has to be in kilograms. And then this is just our change in temperature. So that's our change in temperature. And again, we just make sure that if this is in degrees Celsius, these temperatures need to be in degrees Celsius as well. So that kind of sets up our triangle so that we can kind of go through and solve some problems. So like if we wanted to do a sample problem, okay, say we had, like here we're maybe looking for how much energy is needed to raise the temperature of 2 kilograms of concrete from 10 degrees to 30 degrees. Okay, so I'm going to put that problem down here so we can kind of see this on paper. So how much energy is needed to raise the temp of a 2 kilograms of concrete from 10 degrees Celsius to 30 degrees Celsius. Now, if I kind of follow this and use my kind of guess method on this problem, I know that I'm going to look for my variables, my E, my M, my CP, and my triangle T. So I'm going to look for those values. Now the energy, that was the question mark. I'm going to find that in joules. Okay. My M is the mass. I have 2.0 kilograms. So again, that kilogram is going to tell me I'm going to look for a specific heat. That's going to be in kilograms, joules per kilograms degrees Celsius. Now, the change in temperature. So I want to end at 30. I wanted to start at 10. So the change is 30 minus 10, or 20 degrees Celsius. Okay? And then I'm going to look this value up. So this I have to look up. And in my book, I actually have, again, a little chart here for concrete, and it says it's 880 joules per kilogram degrees Celsius. So this is 880 joules per kilogram degrees Celsius. So now I have my numbers all set. I can just go to my equation. So E equals mCp delta T. My E is what I'm looking for. My M is 2. My CP is 880. My triangle T is 20. So now I just have to go through and do my multiplying. So I grab a calculator. Alright. So we go with 2 times 880 times 2. So that comes out to be 35,200 joules. That's how much energy it's going to take to raise that temperature of that concrete. So again, that's a nice example problem. You're going to have a sheet that you're going to work on today with that. So I thought I'd share that with you. Okay. We're also going to use that when we get into the lab. So now back to the lab. Okay. So we know we've got our mass of our chips. Okay. We've got now to where we were supposed to be doing our analysis. Okay. So the energy of the can. So you need to find the mass of the can. You should have had that from step 2. So this is, look back to step 2. You'll have that mass of the can. And it's going to be the same for all of these. So the mass of the can doesn't change. Now again, specific heat of aluminum, we just looked that value up. That's also in step 2. That's that 0.900. And that's going to stay the same because it's always aluminum. The change in temperature that we're going to have the can experience is going to be based on the highest temperature and the smallest starting temperature. So like this is our T2, this is our T1, and the change in T is just taking this one minus this one. So take our big number, our T2, minus our T1. Okay? And that'll give us what our change in temperature is. So remember, this is just the change in temperature. Now to find the energy absorbed, okay, we're back to our equation here. To find that energy, it's just the mass times the specific heat times the change in temperature. We already have the mass, we have the specific heat, we have the change in temperature. So we multiply these together to get the energy absorbed by the can. So that's how much energy the can ended up getting. Now we go out and we're going to do the same thing for the water. So the mass of the water, you should have that value already as well. That was back here in step 4. Now this is not going to be the same for each. So in other words, you're going to have probably a slightly different number for each of these. The specific heat of water, though, is a value that we're going to have is always the same. That's at 4.184, and that is going to be the same for all of those because it's always water. The change in temperature is going to be the same as the can. So the can's change in temperature, the water's change in temperature is always the same. So we'll be able to look those up from our other part. And again, it's just times these together to get our energy. When we want to get the energy that the chip had, we're going to take the energy of the can. So the can plus the water is going to make the energy of the chip. So that's how we'll find these values here. We're just going to go back, find the mass of the chip. I think that was in step 3. So back here, step 3, we'll get our mass of the chip. We're going to then take, to find the energy per mass, we're going to take our energy, we're going to divide it by the mass of the chip so we can get our joules per gram. And now we have to find a percent error. Okay? So percentage error is the experimental value minus your target divided by your target. We take the absolute value of that. So we don't care whether it's positive or negative. And then we times that by 100, okay, to make it into a percent error. So the experimental value, this is your experiment value right there. So that's your experimental value. Your target value is right here. This is the target value. So you're going to take the experiment minus the target, don't care if it's positive or negative, divided by the target, times it by 100. And that's how you're going to get your percent error. Okay? So make sure you kind of walk through and do that. I'm going to make sure you see that formula again so you can get that. Okay? Then you just have to answer the questions. So there's 2 questions here. You have to make sure you answer. And then you'll be able to be done with your lab. Okay? And you can move on from the lab to the practice problems for 9.1 problems, which will be just like the ones that we did right here. Okay? Good luck, and we will talk again on Thursday. Thursday will be kind of a review to catch up on anything that we're missing. We'll finish whatever notes we didn't get done in 9.2, and then we'll be ready to take the test on Friday. All right? Have fun.